Okay, continuing here with our discussion of solutions. So mentioned back in the first video here for this chapter that we like molarity in terms of chemistry as our unit of concentration because of its connection to moles. And moles, of course, can be connected to a balanced equation. So we can also use molarity when we are evaluating reactions where there are solutions involved in the equation. And just looking at the problem here, right, we've got a solid, sodium hydrogen carbonate, right? So solids we could weigh out, we could get the mass in grams, we could use the molar mass to get to moles. But something like a solution, molar mass doesn't help us here because in addition to the H2SO4, there's solvent here, right? In this case, water. So when you see aqueous as the designation there, anything in equation referenced as aqueous, we would need to think about molarity in terms of converting to moles of that particular component. And molarity will allow us to go from volume to moles or vice versa instead of mass to moles. So we're going to start treating solids that we can weigh out different from solutions where we would have to measure volume instead. So just take a second to appreciate the beauty of this problem. And it's about half of a page. It takes up almost all of the screen here as you're watching the video. And that's just breathtaking, right? Isn't it great to see a nice big word problem like that? So let's see how to tackle it and how we'll use molarity in this problem. Okay, so we've got some sulfuric acid spilled on the bench. Sulfuric acid is H2SO4. We can neutralize the acid by sprinkling sodium hydrogen carbonate on it. That's our other reactant here. And then mopping up the resultant solution. So the resultant solution won't be as corrosive if we dilute and neutralize the acid. Sodium hydrogen carbonate reacts with sulfuric acid as follows. So here's a balanced equation, and it's already balanced. We can use that for this reaction. But then we get into the meat here of the problem. I'm going to slide up just a little bit. Sodium hydrogen carbonate is added until the fizzing due to the formation of CO2 gas stops. So that's one of our products there is a gas. So if we don't see the gas forming, we know the reaction isn't happening anymore. 27 milliliters of 6 molar sulfuric acid was spilled. What is the minimum mass of sodium hydrogen carbonate that must be added? Okay, so here's what we have. We've got the volume of our solution. We've also got its concentration. And again, remember that capital M is moles per liter. So that's how we want to start here. We start with 27 milliliters of our solution. Right? And since it's liters here in molarity, the first step might be, right, change from milliliters to liters. And that is perfectly reasonable. But what I want to show you is a simplification that I like to use. You may find it helpful. You may find you like to do it in 2 steps. They both work the same, so you don't have to do it this way. But recognizing that this is 6 moles per liter of solution, I'm going to change it to 6.0 moles of H2SO4 per every 1,000 milliliters of solution. So I changed liter on the bottom, 1 liter, to 1,000 milliliters, right? Normally we would do that, or at least up to this point, we would do that in a separate step, right? I find this saves a little time instead of writing another step, right? And it makes the presentation a little bit neater here in the sample. But 2 steps in one, sort of, but that gets me to moles of H2SO4, right? So very similar to what we saw in the last chapter, going from grams to moles when we start a problem like this, but again, if it's a solution, it'll be from volume to moles. But once we get to moles of H2SO4, this becomes a very similar problem. With moles, we can now think about what the balanced equation tells us. It tells us 2 moles of sodium hydrogen carbonate are needed to react with 1 mole of sulfuric acid. So that will be the next step we want to put in there. 2 moles of NaHCO3 for every 1 mole of H2SO4. That'll cancel out moles of sulfuric acid. Now we've got moles of sodium hydrogen carbonate. Now the problem actually asked for mass. So to go from moles to mass, that is the molar mass. So 1 mole of sodium hydrogen carbonate, we would want to put on the bottom here. We need to know how much that weighs to go on the top. right? And that will finish off our calculation. So there's one hydrogen, one sodium, one hydrogen, one carbon, and 3 oxygens in sodium hydrogen carbonate. Go to the periodic table. Sodium is 22.99, hydrogen's 1.01, carbon's 12.01, oxygen is 16, so 3 of them would be 48. So, some number carrying there, so just to be safe, I'm going to go to my calculator. And 84.01 is the molar mass of sodium hydrogen carbonate, or sodium bicarbonate. So 84.01 grams per mole. If we multiply all that out, our units are grams of sodium hydrogen carbonate. So how much we would need to soak up this acid spill. So 27 times 6 divided by 1,000 times 2 times 84.01. 27.2, but going all the way back to this initial volume, it's only 2 sig figs. So this is only going to be 2 sig figs as well. So it actually happens to come out to be 27 grams. So about a gram of sodium hydrogen carbonate will neutralize about a milliliter of 6 molar sulfuric acid. Now the concentration of your acid is variable, so this wouldn't always apply to this particular reaction. Okay, but molarity is going to tie right into these types of calculations, just like we've seen in chapter 3 for masses, right? So you just have to be careful, are you using the correct one to describe whatever is happening in your reaction. Solids, you probably want mass. Aqueous solutions, you're going to want volume. Okay? Now, we've got a little more time here. I'm going to go to the next page and just start a little bit of the description here on the next page before we go into a separate video. So we want to start to think about here are what happens when solutes dissolve in solvents. So we want to think about this in terms of just plain dissolving something, but also in terms of chemical reactions. So if I just take an example like sodium chloride, right, we're all familiar with the fact that there's salt water at the beach, and what that means is that sodium chloride will dissolve in water. So sodium chloride is a solid. Now, say I dissolve it in water. So I'm putting water over the arrow here because it's not reacting stoichiometrically with the sodium chloride. It is the solvent in this particular case. But what happens with sodium chloride is when it dissolves in the water, it separates. It separates into sodium cations and chloride anions. And we would change the indication of phase. So sodium chloride solid right now is sodium cations that are aqueous, chloride anions that are aqueous. This is going to be true of most ionic compounds. When they dissolve, they're going to separate into their constituent ions. So we need to be able to evaluate a formula and what ions would be produced if that compound dissolves. Also including polyatomic ions. So salts or ionic compounds with polyatomic ions in them also potentially will break apart when they go into solution. Now, we're going to want to go even further and evaluate mixtures of different ions to determine which sets are soluble in the solution and which aren't, because sometimes there are ionic compounds that don't dissolve in water, and that will lead to us being able to do things like predict the products of particular reactions. So that's going to be the next topic. We're going to talk about solubility rules that I have here, but we'll pick that up in the next video.